Let's look at Prep Test 34 Game 4, which is from June 2001. This is a grouping game where we have 6 doctors, and we're supposed to put each one of the doctors into one of 2 clinics, either Soderton or Ransborough. Each doctor is going to go exactly one of these clinics, right? So everyone has to be used, and each can be used only one time. Because of that, it is a grouping game, but we could further categorize it as a distribution grouping game. The reason we use that term distribution, logically, what we mean, in terms of the logical reason why you're classifying it as a distribution game, it's because every variable has to be used exactly one time. But if you think about it visually, when you think about distributing something, you have a pile of things and you're supposed to move each of those things in the pile somewhere else exactly one time. And then once you've moved all the things in the pile, you're done. But if you still have something in the pile, you need to figure out where to put it. So everyone's going to go one time exactly. That's what makes it a distribution game. In this case, we have a pile of doctors that we're trying to distribute into these 2 clinics. So we're going to have to move each doctor one time and exactly one time. Okay, let's look at the rules and see how the rules are going to help us distribute these variables into groups. So let me just say a couple things about the rules overall. There's 5 rules and they're all conditional, and some of them have compound conditions. So people might be a little bit intimidated by that fact. But actually the rules are written pretty simply. There's not really a lot of confusing language in terms of the way that LSAT gives us the rules. And so if you just keep it neat, then I think you should be fine here. I think the biggest problem would be to come up with a set of rules that you can look at and make deductions from without getting confused as to what you were trying to say and that kind of stuff. So you want to be neat in how you write it down, but I don't think there's that much confusing about the rules themselves. One thing that might be confusing to people, if anything is going to confuse people, I think one thing that could do it is the fact that the rules are written to be specific for each group. So they don't just say that if Juarez and Kudrow can never be in the same clinic. They say if Juarez is at Soderton, for example, in the first rule, they say if Juarez is at Soderton, then Kudrow is at Ransborough. So the action from this rule is specific to Juarez being in Soderton. So you need to keep track of that. Here on the board, I'm using parentheses, so I'm putting the, Juarez is in Soderton, where I'm putting the Soderton in parentheses. On the test, you probably just use subscript. I just use the parentheses because it's easier to do on this board. But on the test, you probably just write J little s, then K little r, okay? And the last thing about the rules generally is that I decided to write the contrapositives here. And the reason is, normally we keep the contrapositives in mind, although some students write them, and there's nothing wrong with that. I tend to just keep them in mind. I know that I may need to look at a rule from its contrapositive angle in order to get an answer, but I normally, can do that kind of in my head. In this case, I decided to write them out because there's only 2 groups. So, for example, looking back at this rule, it says if Juarez is at Soderton, then Kudrow is at Ransborough. The contrapositive of that would be if Kudrow is not at Ransborough, then Juarez is not at Soderton. But what does it mean in this game for Kudrow not to be at Ransborough? It means that Kudrow is going to have to be at Soderton because Kudrow has to be in one or the other. So if he's not or she is not at Ransborough, then Kudrow has to be at Soderton. And by the same token, if Juarez is not at Soderton, then Juarez has to be at Ransborough. So again, the contrapositive of this of the first rule would typically be if Kudrow is not at Ransborough, then Juarez is not at Soderton. But when you translate that, you get if Kudrow is at Soderton, then Juarez has to be at Ransborough. And the fact that we're able to write it like that makes it much more concrete and makes it seem like it's going to be more useful when we actually go to do the game. And then so since I think it's going to be more useful, I figured I'll write it down because it's easier to use when I've written it down. Okay, so let's look at the specific rules. We just looked at the first one, so let's go to the second one. Second rule says Onawa is at Soderton if Juarez is at Ransborough. So if Juarez is at Ransborough, then Onawa is at Soderton. And the contrapositive is if Onawa is not at Soderton, then Juarez is not at Ransborough. Another way of saying that is if Onawa is at Ransborough, then Juarez is at Soderton. Okay? The third rule is where they give us a compound condition for the first time. So they tell us that if Longtree is at Soderton, then both Nance and Palermo are at Ransborough. So if Longtree is at Soderton, then Nance is at Ransborough and Palermo is at Ransborough. Then when we take the contrapositive and translate it, we get if P is at Soderton or N is at Soderton, then L is at R. And I'll just do this explanation one last time, which is, basically this is saying if L is at S, then both of these things have to be true. So if either of these things is not true, if either n is not at R or p is not at R, then L is not at S. So that's another way of writing that. Is another way of saying that if n is not at R or p is not at R is saying if p is at S or n is at S, then L has to be in R. Okay. So the fourth rule says if Nance is at Ransborough, then so is Onawa. So if Nance is at Ransborough, then Onawa is at Ransborough. And the contrapositive translated is if Onawa is at Soderton, then Nance is at Soderton. And finally, the last rule, which is also compound, tells us if Palermo is at Ransborough, then both Kudrow and Onawa are at Soderton. So I wrote that here, and then the contrapositive is if either of these two things is not true, then this is not true. So if K is not at S or O is not at S, then P is not at R. And translated, that means if K is at R or O is at R, then P is at S. All right. So those are the rules. Now let's see if we can put them together deductively to try to come up with some chains that will hopefully help us figure out how to distribute these variables into these two groups. So one thing I should say before we go into the deductions is another thing that arises out of the fact that there are only two groups here is that if a variable is not in one group, it has to be in the other, which means when we want to think about, if we wanted to think about templates in this game, theoretically we could pick any variable and just say that any solution is going to have to include that variable either in Soderton or Ransborough. So if we can, for example, let's take the J, and we say, the first two rules tells us, gives us some action that's going to result no matter where Juarez is. So if Juarez is at Soderton, we get this result, and if Juarez is at Ransborough, we get this result, and then we can build on those results. And any solution is going to have to fit into one of those two templates because Juarez, no matter what solution you're looking at, Juarez is either going to have to be in Soderton or Juarez is going to be at Ransborough. Okay, so now I said theoretically you could pick any variable. You don't want to just pick any variable and put it once in Soderton and once in Ransborough and say, there, I have the whole game in front of me now because I have any solution is going to have to fit into one of these two things. The idea is you want to pick a variable that actually drives some action. And the J looks good at first because, right away they give it to us kind of in a straightforward way where they're like, here's some action that results from J being an S and here's some action that results from J being an R. So you would think to yourself that I can actually draw up templates based upon that action. Now, I'm not going to draw up the templates, but that's the general idea. So let's follow a couple of these out and see what happens. So let's take the first rule. If J is an S, then K is an R. So I started following that out here. So when we get K and R, then basically what we're trying to do now is to look for K being an R as a trigger for some other result so that we can add that to the chain, right? And that's basically always what you're trying to do when you're putting conditional rules together like this. So you're like, okay, if J is an S, then K is an R. Do I know that K being an R triggers anything else? So you look through here, and by the time you get to the bottom, you're like, okay, if K is an R, then P is an S. So you add that to the chain over here. So if J is an S, then K is an R, and if K is an R, then P is an S. And now we look again over here for somewhere where P being an S tells us something else, and that happens here, where they say if P is an S or N is an S, so P being an S would trigger the rule, then L is an R. So we get this result over here, which is L is an R. But then when we look for L being an R triggering something, we realize that it doesn't show up anywhere. Here it's in the necessary condition, but it's not triggering anything, so that doesn't work. And we go through and we don't find anything where L being an R triggers anything, so that would be the end basically of this chain. Okay, now let's skip this one here and go here. So the other situation, the other possibility for J, apart from it being an S, which is what triggered this chain, the other possibility is that J is an R. So let's follow that out. If J is an R, we know that O is an S because of this rule. And then we look for O being an S and see whether it triggers anything. And it does here. So if O is an S, then N is an S. Okay, and that's the only one where O being an S triggers something. So let's follow out what happens if N is an S, which we know is going to have to happen now. So we would be like, N being an S, does that trigger anything? And we go back to this rule, which says if N is an S, then L is going to be an R. So here we go from N being an S to L being an R. Okay, and that kind of ends because nothing really builds off of L being an R. So that kind of ends that chain as well. And you'll notice that in the first two chains we looked at, and again, I did this on purpose and I may have even just said it, in one case J was an S, in the other case J was an R. So any solution is going to have to fall into one of these two chains. Okay, so some of you may have noticed something already about what always has to be true, and it's based on the idea that I was just talking about, which is that we just discussed uh, the two templates basically that any solution is going to have to fall into. So so you know, if there was a result in common from J being an S and J being an R, then that result would always have to be true, because any solution is going to have to either include J being an S or J being an R. Hopefully that makes sense. And you know, we'll get to that in a second. I basically just drew it out for you, so hopefully you can think of it on your own. But we'll get to it in a second, which variable or something we can always know for a fact, no matter what solution we're looking at. But let's continue on with the deductions here. This I basically, and this second one, okay, I basically just noticed that K being an S triggers J being an R, and then you know, when J's an R, we just discussed what happens then. So this is basically, this second deduction is basically just this third deduction, but adding the KS in the front, because I noticed that the KS would trigger the JR chain. All right. So let's go to this fourth deduction, which starts with PR. And basically what I was doing was, you know, taking these rules over here and drawing out the result, following them out, and seeing what else I could figure out besides what they told me explicitly. So if P is an R, then we know two things. We know that K is an S and O is an S. Okay? So we're like, all right, if P is an R, K is an S, and O is an S. And then what else can we know? So let's start with one of them. Let's start with the fact that O is an S. Does that tell us anything? And again, we go back here. And if O is an S, then that tells us that N is an S. So we can do that. We should check whether K being an S tells us anything also. And when we look through, we notice that here, actually, K being an S tells us that J is going to be an R. So I should have actually written here that N being an S is not the only thing that results. We also know that J is going to be an R. Okay? And then when J is an R, we should know actually everything that occurs here. So when J is an R, we know O is an S, which we already wrote here. We know N is an S, which we already wrote here. And we know that L is an R, so that's why we have to add this here. Okay, this L being an R can result from either actually N being an S or J being an R. All right, but it's important to understand that once you get this J being an R, then everything that followed originally when you were trying to think about what happens when J is an R has to happen in this solution also. Okay, so you need to make sure that they match up like that. Okay, so let's look at this last deduction over here. And it just starts from this rule, which came from here. So they say if N is in Ransborough, then O is in Ransborough. So we want to know what's going to happen if, you know, what else is going to happen in this case. So if N is at Ransborough, then O is at Ransborough. So we look over here for other things that are triggered by O being in Ransborough. And there are actually two things that follow. One is here, which is if O is in Ransborough, then P is in S. Okay, so I added that here. And then the other thing that follows is that if O is in Ransborough, then J is in S. So I added that here. Okay, and those are the only two things that follow if O is in Ransborough, but now we want to know, you know, what might follow from P being an S or J being an S. So again, we look here, and we're going to do it both at the same time. So P and S or J and S. So here we have J and S, and we know that if J is an S, then K is going to be an R. Okay, and the other thing was we're still looking for P being an S. And so P being an S, we're looking, here we go. P being an S, L is an R. So we added the L being an R over here. Okay, so we knew that K was going to be an R because that's what happens when J is an S. And we knew that L was going to be an R because that has to happen when P is an S. And that kind of wraps up this deduction chain also. Okay, so now let's go to this and we'll end the video here. Which variable must always be in R? I'm going to talk about this a little bit more in the next video, but I'm running out of time, and I do want to kind of wrap this up and end with this point, which is that which variable must always be in R? Well, let's just take it as simple as possible. We know that when J is an S, then L is going to be an R. And we know that when J is an R, then L is going to be an R. So remember, J and S and J and R encompass all solutions. So in any solution, what's going to have to be in common is that L is going to be an R. Okay? So the answer to this question is that L is always an R. And that's exciting. All right, I'll see you in the next video.